This is the Geospatial CriminalTracker demo. Convicted offenders, as well as suspects awaiting trial, are frequently required to wear ankle bracelet monitors. A centralized tracking system for these monitors needs to handle large amounts of incoming data and must be alerted to unwanted behavior, such as offenders entering prohibited locations or being physically present with other offenders or protected targets. Making these determinations require resources and judgment that must be performed at the time of the event. Automating these decisions will greatly benefit law enforcement, allowing relatively few monitors for several tracked targets. Our CriminalTracker system collects data streamed from multiple sources. It performs automated analysis on this data at the moment it is reported, and then sends the data and alerts to registered user interfaces with only sub-second processing time. Currently, the CriminalTracker uses spatial queries to detect when offenders come within a certain distance of each other. This distance can be set dynamically. It will also detect when offenders approach restricted locations. The locations are stored in a static database, can be updated during system operation, and the distance where an alert is triggered can also be set to any distance. The tracker system has implemented other queries, such as being able to detect the nearest restricted zones to any offender within a certain range. Our demonstration UI, however, does not show the results of such queries as it is focused on real-time events. In order to be compatible with a wide number of possible front ends, we have decided to use the JSON object protocol to output our data. The CriminalTracker can listen to a large number of independent data sources and is capable of processing several incoming events per second. The number of queries that can be performed on the data is easily extendable, as well as the variety of static data that can be employed.
This is the Geospatial CriminalTracker user interface. In this demo, simulated GPS traces are used to give an overview of the system. In the left column, a stream displays alerts in real time as they are pushed from Stream Insight. An alert can occur when a criminal enters an area that is restricted to him, triggering a restricted zone alert. Or a proximity alert can occur when multiple criminals gather too close to one another. On the right-hand column is a map that displays real-time activity of criminals and restricted zones. Currently, there are 3 restricted zones displayed, all of which are areas 2 criminals cannot go. These static areas are stored in the database and pushed to the user interface to be displayed on the map. These are the same areas that are used to calculate the occurrence of an alert. The 2 criminals are represented as points, and locations are updated in real time as their locations change. Criminal 10 is the bottom point, and Criminal 20 is the top point. These locations are also pushed from Stream Insight. At the beginning of the scenario, both criminals begin heading towards the restricted zones. Criminal 10 triggers a restricted zone violation when he enters UW1, and soon after, Criminal 20 triggers another restricted zone violation when he enters the library. We'll now move on to the next portion of the demo. Both offenders trigger an alert as one enters UW1 and the other enters UW2. The criminals then begin leaving, at which time they get within 1 meter of each other, triggering a proximity alert. Both criminals then leave the scene.
Real-time streaming data processing is performed by Stream Insight, using continuous queries that also reference SQL Server spatial and non-spatial data. The architecture demonstrates interoperability by employing multiple technologies, such as Java, C#, and JavaScript. And its well-defined contracts allow for a variety of other technologies to be used for event sources and UI output. Incoming network communication and outgoing communication is multi-threaded to handle multiple ankle bracelets and client UIs. GPS traces are transmitted from the ankle bracelet using HTTP to the trace listener. CriminalTracker is the main application, containing the Stream Insight server, which acts as the observer receiving each trace. All traces are processed by CriminalTracker using SQL Server data and user-defined functions, and pushed to the UI and logged to the database. Possible future work includes creating more queries to detect new alerts, as well as a configuration user interface, in which a dispatcher can add, remove, and modify offenders, users, and locations. In conclusion, the CriminalTracker demonstrates data stream processing of GPS traces to detect alerts using multiple technologies to display the alerts and traces on a map interface, all in real time.